Now, let's look at another method for approximating area, the right-endpoint approximation. This method is very similar to the left-endpoint method, but with one key difference. We use the right side of each interval to determine the height of each rectangle. Let's look at the graph here. We have a total of 4 rectangles, and the width of each rectangle is the same, which is delta x. To find the length of the first rectangle, we start at the right endpoint and go straight up to the curve. This gives us the length of the first rectangle, which is f of x1. To find the length of the second rectangle, we start at the right endpoint and go straight up. This is f of x2. To find the length of the third rectangle, we begin at the right endpoint, go straight up to the curve. This is f of x3. And to find the length of the fourth rectangle, we start at the right endpoint, go straight up. This is f of x4. The area of the first rectangle is delta x times f of x1. The area of the second rectangle is delta x times f of x2. The area of the third rectangle is delta x times f of x3. And the area of the fourth rectangle is delta x times f of x4. Notice something important? The rectangles are mostly above the curve. This happens because the function is increasing. So when you use the right endpoint, we are using the larger y value compared to the rest of the interval. This means the right endpoint method will overestimate the area if the function is increasing. So the formula is r sub n equals the sum from I equals 1 to n of f of xi times delta x, where delta x is the width of each rectangle and f of xi is the length of each rectangle. And r sub n represents the right endpoint approximation. Now, let's apply this to the same example. We're given f of x equals x squared, the interval from 0 to 2, and n is 4. First, let's find delta x. Delta x is b minus a over n. b is 2, a is 0, and n is 4. So I have 2 minus 0 over 4, which is 0.5. Next, let's find the x values. So we have x0, x1, x2, x3, x4, where x0 is a, which is 0. x4 is b, which is 2. The distance between two x values is delta x, which is 0.5. When x0 is 0, to find x1, I take 0 plus 0.5, which is 0.5. To find x2, I take 0.5 plus 0.5, which is 1. To find x3, I take 1 plus 0.5, which is 1.5. For the right-endpoint method, we use x1, x2, x3, and x4. Next, set up the sum. So I have r sub 4 equals the sum from I equals 1 to 4 of f of xi times 0.5. Now, we are going to expand this. We have 0.5 times the sum of f of xi from I equals 1 to 4, which means we have f of x1 plus f of x2 plus f of x3 plus f of x4. And x1 is 0.5, x2 is 1, x3 is 1.5, x4 is 2. So we are going to plug these values in. And that becomes 0.5 times f of 0.5 plus f of 1 plus f of 1.5 plus f of 2. And f of x is x squared. So f of 0.5 is 0.5 squared. F of 1 is 1 squared. F of 1.5 is 1.5 squared. And f of 2 is 2 squared. And we are going to add these values, then multiply by 0.5, and we get 3.75. Now, let's look at the graph. Look at the top of each rectangle. Most of the rectangles are above the curve. This happens because the function is increasing, so the value at the right endpoint is larger than the rest of the values in that interval. That means each rectangle is too tall, so when we add them all together, the total area is too big. So from the graph, we can see that the right endpoint approximation gives an overestimate of the true area. Now let's compare this with the left endpoint result. The right sum is 3.75 and the left sum was 1.75. The left sum is too small and the right sum is too big. So the left sum tends to underestimate the area. And the right sum tends to overestimate the area. As n increases, both become closer to the actual area. Now, we are going to bring everything together with one very important idea in calculus, Riemann sums. So far, we've been using the left endpoints, the right endpoints, but now we are going to make it more general. Instead of always choosing the left or the right, we can choose any point in each interval. We write this as the sum from I equals 1 to n of f of xi star times delta x. Now, let's understand what that means. Imagine we have an interval from x0 to x1. Before, we picked the left endpoint or the right endpoint. But now, we can pick any point inside the interval. It could be in the middle, it could be closer to the left, or it could be closer to the right. So xi star just means a point somewhere inside the interval. That means the height of each rectangle comes from that chosen point. A Riemann sum is the sum of the areas of rectangles used to approximate the area under a curve. So this is just a more flexible way of doing what we have already been doing. Now, here is the most important idea. As n gets bigger and bigger, the area is the limit as n approaches infinity of the sum of f of xi star times delta x. This means we use more and more rectangles. Each rectangle becomes thinner and the approximation gets better and better. This gives the exact area. So we are no longer approximating. We are now finding the true area under the curve.